You can see my slides. So
Sure.
the the session yesterday, was titled "What This is not breaking news," and I kind of wanted to make a the point that as long as engineers have had data, they've tried to analyze it. I mean, so you can go go back decades, and the first when we didn't have a whole lot of data, and maybe we were managing trying to do this analysis in much more narrowed focus kind of functional kind of ways, but the fact of engineering analytics is something we've always done. I mean, that's what engineers do. That's what some of the operational analysts do. As we were trying to use the data to create models to understand the performance of our physical systems, and we were trying to build models that would help us understand maybe glitches in performance, maybe do some forensics about why something failed, or we were trying to build a model to understand what was going to happen tomorrow. So all of that sort of call that engineering analytics is absolutely what engineers have always done. So that's not new. What is new is we and now have some very, very powerful tools built on increased computer computational capabilities. The graphics processing units, the GPUs, that actually didn't come from oil and gas at all. It came from the gaming engines, right? NVIDIA got it started, putting fast computational chips into to games so that we could shoot down the alien spacecrafts, right? So we weren't trying to find oil and gas. We were just playing around with the increased graphics processing. So again, it's this idea of a lot of technology innovations have come from outside the industry, and the industry is now faced with, and a lot of this stuff around data science has been developed for many, many different industries by not the Schlumbergers and the Halliburtons, but by the Amazons and the Microsofts. And so we're now not in a role of invention, which, most of my career, the oil and gas industries with their data, with their laboratories, invented the technologies they used in the oil field. We are now in the world of adoption, and we're trying to take advances that are happening outside our industry and figure out how can we apply them within our industry. So the big deal about data science is not only the increased computational capability. Sorry about that. Uh, but the whole concept of seeing things that are happening outside our industry and figuring out how to use it on our problems, whether it's a reservoir characterization problem, a drilling problem, a completion problem, or an economic problem over the life cycle, whatever it is as we go through this. So it is a different kind of an idea where we're now not the inventors but the learners as we go through this. Well, one of the things, it's hard to pick up a journal, technical journal, or even a business, kind of magazine and not have, just half the articles written about artificial intelligence by all kinds of different people. Well, and I think one of the kind of ironic and maybe even funny things about it is everybody now is an expert in AI, whether they know what they're talking about or not. So one of the things I would kind of recommend to you that you all be a little bit of skeptics with regard to what you read. I mean, advanced mathematics and statistics to really understand the programming takes a while. I mean, yeah, you can learn, you can go on a YouTube channel and learn how the basics of Python programming because that there are these, I think, very useful toolkits like Python, which is called a low code programming language. So it's not like C++, it's not like JavaScript or anything in the computer science side of things where essentially you are writing code to control every aspect of the processing, kind of flow. And you end up writing hundreds and hundreds of lines of code for a problem. These low code environments with Python, R is another one. There's several. out there. They're essentially just assemblers of open source subroutine libraries that already exist. So essentially, you're not writing the whole program. You're just assembling. Well, I'm going to call something from Panda to ingest my data. I'm going to call something from SciScript to do this. I'm going to call something from another subroutine library to do my graphics displays. So that helps, and that improves the ability of an engineer who's not a computer programmer by trade in order to try to create these jobs or to use someone else's script that they have tried to do this. So in a way, yes, you can learn a lot of the basic tools and techniques for using artificial intelligence in a much faster way than say that if you were going to dive right into the hardcore computer programming. But to understand really what you're doing with the data, as we kind of talked about last time, what you're doing with the problem, how are you going to go about displaying it. There's no overnight success in AI. It still takes a lot of time and effort as you go do this. But a lot of people, just because it's such a hyped issue these days, everybody wants to be an AI expert. In three looking at a 3 hour YouTube video. So, and that's not true. I mean, that the people and don't claim this for yourself either. It's a journey. It's going to take work. It is important. It is worth the effort, but it is not something you're going to be an overnight success. I wanted to, I'm gonna, in this lecture, I'm going to kind of bring up about some of the words from some people who are more expert at this stuff than I am. I am an avowed generalist. I know a little bit about a lot of things. I'm not one of these specialist experts that knows a whole lot about a single sort of thing. So I'm gonna rely on the words of some people that I believe are real experts in this kind of field in order to try to talk about what are the key messages, etc. So the first one here is just about the importance of collaboration. The most successful companies that I have seen, oil and gas companies, or oil and gas service companies, or whatever that, or tech companies that are trying to build products for oil and gas, they're not run by some senior super digital artificial intelligent wizard, data science wizard. They're run by teams, and yes, they have the really really good programmers, and I think this is one of the things. A really good programmer is not a little bit better than the average programmer. An expert programmer is 100 times better than the average programmer. So you want someone who can really write the code. But those people usually don't understand the statistical modeling approaches, which is another skill set in all of this stuff, usually a statistician or somebody from applied mathematics fields. And then those folks don't really understand the data used in the oil and gas industry. And often they aren't the domain expert that understands the problem trying to be solved. So the best idea is not to create all of this knowledge and skill in one person, but to create a team. And that team drives the idea of collaboration. And and maybe your code is not developed in your company. Maybe it's developed. You do that as a commercial product, kind of procurement that you use somebody else's tools, which is fine. But you got this idea of we're having to try to figure out how to collaborate, and with this we have to develop some very important things like common understanding of terms. And that is one of the kind of real challenges here. It's not common understanding of what a code does. It's common understanding of what the word well is, or production history, or some of the simple things that we talk about that a petroleum engineer would know through their training. But now that doesn't mean the programmer knows what those words mean, or the statistician knows what those words mean. And the data people definitely know what those words mean because they are managing that data. However, they do it in a data warehouse or in a data lake or other things we talked about before. So collaboration is important, and collaboration requires communication. It requires this goal of enabling interoperability. And that's kind of the magic term as we go through all the rest of this stuff. We are now trying to see a bigger picture. We're now trying to integrate data from all parts of a value chain of oil and gas. And that is, really important to gain these new insights to really apply the bigger digital twin models we talked about. We're trying to essentially do asset optimization, not just where we say my asset is a well, and then I want to optimize the drilling time of a well. We're talking about the whole life cycle of the asset, from exploration and discovery through to almost abandonment. So now we're looking at bigger problems. We have different kinds of data. We have the tools to do it. I mean, it's not that this is impossible, but it is a new, different kind of problem that is enabled because of data science and is enabled because of the new computer capabilities as we go through this. So the magic word is, I mean, there's several magic words: collaboration, communication, interoperability. I don't know if you want to boil it down into one, it's integration. And that's not easy to do. And it's much easier to say I'm an AI expert and I can optimize my Python code to solve XYZ problem. But to integrate all of the aspects across a workflow or systems view of the oil field, that's not trivial. That's not something you get in 3 hours from a YouTube video. So the expert that I'm going to rely on here a lot is an individual by the name of Satish Sankaran, and he did an awful lot of really good work at Anadarko, and now he's in a consulting company. But just I'm involved in the board of a technical section from the Society of Petroleum Engineers called Data Science and Engineering Analytics. So DSEATS is kind of the acronym that within the SP committee. I'd recommend that to you to join as a student member or as a practicing engineer. And it really, is a community that is really focused on a lot of these things. We recently interviewed Dr. Sankaran as part of our first quarter 2024 newsletter. Every one of I'm on the newsletter subcommittee, and we try every quarter to publish this newsletter. And every quarter we try to interview one of the experts. And we've got I think a really good track record now here of a couple of years of these newsletters. This technical section's only been going on for a couple of years, and so we want to try to build up this knowledge base for a lot of people to try to take advantage of. So and I'm not gonna read all the words from Dr. Sankaran, but in a sense he's talking about making decisions under uncertainties. And I think that's one of the key things here around data science is no again, if we're not all 100% physics based, we don't have this chance to be precise. We don't have this chance to be what I'll call deterministic. The answer isn't just one number that we are very, very sure of. The answer is a probability of results. And so that idea of, and a lot of the factors, the input parameters that we have in these models are probabilistic sort of estimates. So dealing with uncertainties is now a fact of life. And then you can say, well, do we know the porosity of the rock in the reservoir? Well, it's not 18.4%. It's somewhere between 15% and 24%. And there's this distribution curve of these different samples that we have taken. So even a key parameter like porosity would be a range of values. Porosity, or permeability, a range of ones. Reservoir pressure, fluid mix. All of those sort of things now are not just a number to plug into an equation. They are distributions. And these distributions that are multiplied together give us more distributions, right? With regard to that. So we are now dealing with a concept of the results coming out being probabilistic, not deterministic. And I think this is a key point that Dr. Sankaran makes. And now we have to make a decision under uncertainties. We don't know for sure that it's six. It could be five, it could be nine. And what is the possibility of what we would do in under those different sort of circumstances? So we have mental models. This is one of the advantages of humans, that we can essentially deal with these uncertainties. We can deal with these models, and we can make rational judgments, from that, that kind of an approach. So essentially, we are taking all of this data now that we have, the big data challenge I talked about yesterday, and we are dealing with them in terms of distributions, not data points. We are building statistical models that are physics constrained, and we'll talk about the hybrid models a little bit more. But and in that we are now we have that's a lot of calculations. We broke in Excel. You can't do this on Excel anymore because there are just too many variations of what we're trying to do. We're not talking about hundreds of calculations. We're talking about billions of calculations in order to try to deal with all of these distributions. So there's no way we can, as a human being, are going to do that. But the good news is we don't have to, right? We've got the large computers that are being able to deal with this for us. But in there, and we kind of this in this newsletter we talked about, and Dr. Sankaran and others were saying that the industry's three key issues around data science. One is the lack of understanding of relevant subsurface physics, i.e., we're now dealing with models that don't, fit the basic assumptions of Newtonian fluid flow through porous media, right? Going way back to, the earliest physics understandings of reservoir performance. But a shale doesn't behave like that. A reservoir that's very tight, but that we fracture doesn't behave like that. And now we are dealing with subsurface um, reservoirs where we don't particularly 100% understand the physics anymore. So we have to approximate it. And if you have a lot of data and you have some of these statistical techniques, i.e., machine learning, then we are going to be able to create relevant models. Well, we don't always collect the right data. We're collecting a lot of data. There's no doubt about that. But sometimes we don't have the data that we would like to have in order to get some of these correlations. And that's one thing here that just machine learning or artificial intelligence in general is an absolutely fantastic correlation engine. It will find patterns in the data that we feed it. And the more the data, maybe the more relevant the correlations. But it is not a causation solution like physics may tell us to try to do. So the correlations may be false. It is still very possible to crunch all of these numbers and come up with an answer that's not right. And that's because correlation is not causation. That's one of the basic kind of principles in statistical analysis. Is sometimes we put together all the wrong data that is related to something else, but is not to a causation solution to our problem here. So massive correlation. You will get an answer. You will get a model. You can build a model from this data that would represent a certain amount of the input data flow that we have in a certain amount of the history. But is it right? That's where I think we need the human critical thinking skills to try to, kind of as the last check to make sure that these models make sense, because we already know from even non-oil and gas applications that these models can what's now called hallucinate, right? It can come up with a silly answer. And it's still based on the same data, based on the same processing technique, but the answer is not right. So can we understand that? And it's usually based on putting the wrong data into it. And kind of the third thing here is the traditional modeling approaches are not keeping pace with decision-making demands. Management now, with all of this computer power and all of this investment in these models, they don't want an answer that says, well, once a year I want to make a capital budget. They're saying, how should we tweak our water flood injection pattern this week? So we're quickening the pace of decision making because of these techniques. And that's what we need, models that are dynamic enough or adaptive enough in order to aspire to meet management's expectations about faster decision making. So again, going back to Dr. Sankaran and some of the interview, and if you want to look at the whole interview that we have with Dr. Sankaran, you can check out the newsletter on the SB website. But essentially, we want to build. We're now moving out of the physics because we don't understand the physics that well. We are now substituting a data-driven model, but we don't want to leave physics. We don't want to leave the constraints that are there because that helps us to avoid some of the hallucinations, some of the statistical correlations that are that become just tremendously weird outliers with regard to the results. So the hybrid model is a data, and we kind of had this in the question at the beginning. It is not data statistical models improving our physics. It is our physics models and understanding constraining our statistical data-driven models. And that's kind of where we're headed right now with regard to this stuff. And this applying data analytics, the gaps in reservoir surveillance and management can be filled to optimize oil field development. We can look at bigger pictures, we can make better decisions, and over a larger part of the problem to create greater value. And so the two big things here is greater new insights to create greater value, and our always technique to do it at a lower cost and safer, right, with regard to these things. So, and that the safer has to do with the idea that more and more of the oil field is now automated. There's not a human in a dangerous position within the drilling platform or doing maintenance in a production field or whatever, where there is certainly pressure and explosive, kind of fluids. And I mean, the oil field can be a dangerous place. So we need to do it safely, number one, and then we need to do it efficiently. So there's a drive for efficiency and there's a drive for new understandings of more complex reservoirs and a more complete view of the system of how do you create value within the oil field. It isn't just producing more oil and gas. It isn't just drilling more wells. And I have an example here talking about just drilling more wells is no longer the goal. It's to create wells that produce more oil. And with it, maybe I don't have to drill more wells. So clearly, if you go through all of these different things, we are beginning to see the problem in a broader way, in a more systems kind of way. But with that, there's a lot more parameters. There's a lot more uncertainty. These models are getting more and more complicated. This is working through this thing. We are not reducing complexity. We are increasing complexity significantly. But then that presents the challenge in our display of the data results, like we talked about yesterday. We have to make all of this complexity look simple enough to be able for people who didn't dive into all of those steps in our processing flow. Again, they don't care, right? But they just want to know what the results are. We're going to show them these choices that they can make in terms of the decision making in a way that reduces the complexity to something that's more understandable. So the integration of this data-driven methods with physics is the goal. The goal is not it is not physics or statistics. The whole part of this data science approach is physics and statistics. And if you get that, then you appreciate the importance of hybrid models. Well, I've used this slide before in previous talks, and I think it's still true. And I think we still fall into some of the traps when we think about the digital oil field of the future. We still kind of tend to focus on the technology or the IT aspects of it, or maybe automation aspects of it. It really is still about engineering. I mean, it is using some of this technology and all this new data we've been able to collect and use, and it's all of the automation, things that we can, take people out of harm's way. We can improve efficiencies with known processes. We can put that into the equipment now. But essentially, it's still about engineering. And when we forget that, I think we're going off in the wrong direction. Also, there's a human change management issue around all of these things that we can build fantastic models, but will operation engineers believe them? Will they apply them? Will they use them in terms of what they're trying to do? So, we're just saying, well, don't worry, well, I use Python on the latest version of Python on it. They're going to say, I don't know what you're talking about. And so clearly still have to explain the results of these new analytics to the people that are in the field. And we always think, well, on the next, I didn't get everything I wanted to in this project. I'll do it on the next project where I don't have so many constraints of time and budget. Well, major capital projects are those greenfield next projects, but often they have their own constraints. And we still have trouble introducing some of these new ways of working that we have worked out on our digital twin that we're very confident is a better way of doing things. It's still hard in the change management issues to put that into the next project plan. Data management is worse than you think. And this is not a criticism of those that are trying to manage all of this big data, this increasing volume and variety and velocity of data. They are doing a good job. They are improving their role incrementally, but we're throwing data at them that growth is exponentially. So it isn't that data management is getting worse. It is getting further away from the ideal than we need it to be because of the tremendous explosion of data, the data tsunami that is hitting our companies of all the data that is available and all the different types of data that is available make it really hard on the data management people to keep it structured. And that's where we've gone from ETL to ELT. And the idea that we're now having to hand off some of the data management issues to the analysts because the data prep people are overwhelmed. And so now that's another task of your analyst is to pick and choose trusted data. It is to reformat data into a common integrated sort of format. And that's what I mean by data management's worse than you think. You think it might be easier just to sit down and write code. Well, no, that's just one of many tasks that we're trying to talk about. And we get a lot of salesmen who come into the office with talk about brand new data capabilities, and a lot of it's amazing. I mean, it really is amazing, but it's not the field, it's not the technology in the field that you're trying to work on. I mean, we change our smartphones out every year, right? There's when a new model comes in, it's got a better camera, so we're going to buy a new smartphone. But the SCADA systems we have in the field may last the entire economic lifetime of the field, or we may change them every 20 or 30 years when there's a new way of developing, say a water flood or other enhanced oil recovery sort of technique. So we don't change some of this technology out as quickly as we do as consumers and in the industrial kind of realm. So dealing with the deployed technology sometimes brings some realities that you don't have everything that you want, and you don't have everything that you could have based on the new capabilities, but that's not, we don't change them that quickly. And again, it's more than just numbers. It is people who understand the models, people who can build the models, people who can run the models and look for outliers and things like that. And that requires a fundamental improvement in what I'll call digital literacy of almost the entire staff. It's not the few guys and gals that are sitting at headquarters writing this code. It is a little bit of understanding of all of these models throughout all of the team, the staffs that are out there. And we have to be able to find time to sit them down to get them to try to want to learn. And the lessons that may happen from manufacturing, from some of the commercials, some of the supply chain systems, et cetera, they're still hard to learn in upstream oil and gas, where we've got a very strong not invented here. They don't understand my realities, kind of a model. But there are infrastructure technology. I mean, the digital oil field of the future is often referred to as integrated operations by the North Sea operators in Norway and Britain and the rest of that. And this is an area that kind of developed a little bit later than some of the other, say, oil basins within the United States. And so, therefore, new technology kind of came hand in hand with a lot of the new field developments. So you've got infrastructure, communications capabilities that are really pretty first class, and with that, the say the Norwegian offshore, they are able to unman a lot of offshore facilities and move the data to an onshore control system center, and whether it's in Bergen or Stavanger or Trondheim or whatever, and essentially run the field more like a lights out manufacturing factory. That, is a tremendous amount of analytics has gone into that, but a real emphasis on the data, on the communication capabilities, etc. So you are now being able to see the whole basis, not just a field, but whole basins being connected. And we talked about the importance of connected IoTs and connection, capabilities with regard to the digital oil field. So clearly, some of this stuff is happening, and you could go to some places where the futures, kind of looks like it's already here with some of these new, kind of capabilities as we have that. So, there's it does exist. This is not science fiction. This is not maybe someday. This is in some places it is today. And as we look um, at this idea of the connectivity and fields, the field getting smarter, we'll put it that way, the field equipment becoming smarter. It used to be the days where we would collect data in the field, then we would send it to the central decision support room at headquarters. It would build the models. It would just send the instructions out to the field, and that was digital oil field 1.0. Well, digital oil field maybe 2.0 is all of these edge processing, the architectures I talked about at the last one. But maybe digital oil field 4.0 is that model that we put in the actuator on the smart pump in the field is actually run by some sort of artificial intelligence algorithm. And with that, it not only executes just set point commands that we gave it in the model, maybe that it now can learn from its changing environment. And that would be digital oil field 4.0, is when you have the idea of that the smart equipment in the field learns. And that's the magic in data science here. In the artificial intelligence, you don't have a model that just does the same thing over and over again, like I told it. That's automation. But when those algorithms can learn from changing pressures and temperatures and gas oil ratios and water produce water flow, all when the equipment changes because of changing dynamics in the oil field, it is learning. And when it is learning, it's taking that next step towards the ideal where it potentially becomes autonomous. And autonomous, that's where we're taking lessons from space exploration and putting it into the oil field. So this stuff continues. And over the, say, 20 years that I've been involved with this digital oil field sort of concept, I think it really has progressed at least 3 generations from 1.0 to 4.0. Now, not a lot of fields are 4.0 right now, but they're starting to see some of the aspects of it coming on. So back to Dr. Sankaran. And I think he points out a really important one, that one of the really big deals that changed our use of engineering analytics, which I said we've always been doing, into this higher level of statistical maturity is the fact that we're dealing with shale, or as an unconventional reservoir in many parts of the world, particularly North America. But it's kind of, there are shale fields all over the world. Because this reservoir no longer acts like a conventional reservoir. And therefore, if we have to put physics to the side a little bit, we have statistics as our basic kind of opportunity to try to model these reservoirs. And with that, and the fact that we are gathering a whole lot of data while we are developing these fields, we now are be able to try to get to the same reservoir characterization and optimization goals that we've had with conventional reservoirs. With traditional reservoir simulators, we now have new reservoir simulators trying to do the same things, but develop more on statistics and hybrid models rather than pure physics models. So this whole idea of production optimization in unconventional fields allows us to use data science in a very basic, kind of way. And, well, obviously with everything coming faster and we're getting more data and getting more data quicker, we are also obviously making a lot of decisions as we go through this, in a much faster kind of way. It is not changing it every year, it is changing it every week. And so a lot of these techniques, and even the machine equipment, are changing some of their behaviors every hour, every minute. So the whole quickening of the decision making of all of these things are really kind of important. So, and he talks about two specific applications of these hybrid models being production optimization. That's all the way from drilling to completion techniques, fracking techniques, to production techniques, when to put on artificial lift, how to deal with produced water, all of those sorts of problems around production optimization and field development planning of these unconventional fields. That really changed the game and said, well, it wasn't a nice thing to have. These new analytical tools were things that we had to have to be able to get on top of the new problems. Well, just a couple things about uncertainty. And maybe statistics wasn't your favorite class, or maybe you haven't taken it yet if you're a student. But clearly now it becomes very, very important. Because the answer isn't just six. It is some sort of distribution of results representing, again, I think a great example is the porosity of the rock that we are dealing with. It isn't a number, it is a distribution. And all of those things, if you assume it's 20 and it really is 16%, then you are overestimating the results and you're going to get bad results. If you think it is 18 and it really is 24, you are underestimating the results. So I have to put all of this data in. There's no one number that represents the truth. There is a distribution that represents the truth. And as we go into some of these decision making, kind of techniques, the whole idea of the decision tree and the probabilities around a lot of that is, not all the time are things going to work out well. So you have to put probabilities on some of the possible results of some of the possible combinations of factors, including price, because the engineer is not just solving this thing to have a beautiful engineering answer. He wants a good economic answer. He wants to make money. And so as you go through all the rest of these things, these decision trees are involved with other sorts of parameters like commodity prices. And it might be one price for crude oil, another price for natural gas, a cost for getting rid of produced water, et cetera, et cetera. And all those things become part of the economic equation of the decisions that we're trying to make. And we build that into the model too. And now we get these things like probability distribution curves. And so you go into your boss one day off all of your models and you give him the most likely answer, which is frequently called a P50 answer. The 50% probability it's higher, 50% probability it's lower. You give him a P50 result, and he says, "Excuse me, I want a higher answer. I want the P80 answer all the time." And you have to gently explain to him that he doesn't understand probability theory, and essentially said you're going to have to change the entire production flow to get a much higher result. So clearly understanding probabilities and uncertainty, the whole statistical kind of theory, the new tools, how to build models, the winnowing down the data to get to just the right, attributes, the principal component, analysis sort of models. All of that are now critical skills. Yes, and then you have to program into your Python artificial neural network all of that stuff. But you still have to be a good petroleum engineer. You still have to understand, all of the things that goes on with fluid flow through your reservoir. So we're not throwing away any of your education. We're just adding a couple of other disciplines that you need to understand. Well, you hear a lot of terms. Artificial intelligence, essentially, simply put, it's any technique which enables a computer to mimic human behavior. And the key thing about the human behavior we are trying to put in these algorithms is the ability to learn from their environment and not just execute set commands that you have predetermined and you put into an automation system. That's different. That is typical traditional engineering analytics. Now we want the algorithm to learn. Why? Because it is set in there managing a dynamic environment. So the answer you put in at the beginning of the field is not the right answer 3 years later. The field has changed. You want the algorithms to change. And, the idea of how humans will work with these smarter and smarter systems. Um, Machine learning is just one of the ways that it's kind of a subset of artificial intelligence as you go through that. It is one of those statistical, techniques that we can help an algorithm to learn without being, as programmed to do this and then that and then something else. That's the old way. The machine learning now tries to build that. And of course, one of the favorite techniques here is the artificial neural network, where essentially we set up the machine code to mimic the neuron processing in our brains. That's the neural network part of this thing, as we are setting up these algorithms to mimic how our brain works, how our brain receives information, how it processes it and makes kind of information through that. That's a neural network. Now there's the random forest, there's surrogate vector machines, there are other sorts of techniques essentially in machine learning, but neural nets one is the most specifically that to mirror the behavior of the human brain. And deep learning is just one where we take a very, very complicated multi-layer neural network and process just a ton of data in order to try to build our models with regard to this stuff. And that we're getting closer and closer to this convolutional um, um, uh, AI, it's kind of techniques that are the Chat GPT things that they're working right now. And again, this is where the model is now actually going to not answer us like a search engine and give us here is the top ranked website to go to answer our question. It's answering us in text. It can answer us in speech. It can begin to work with us in our own language with regard to that human machine interface. Well, just a couple of definitions here, and you can get these from a number of websites these days. But an artificial neural network is a computational model based on the structure and functions of a biological neural network, i.e., us, our brains, as we kind of go through that. So information that flows through the networks affects the structure of the ANN because a neural network changes or learns based on weighting functions with regard to all these nodes. So clearly, this is our brain companion with regard to an algorithmic sort of structure as you go through this. Deep learning is, again, we're trying to simulate the behavior of the human brain because we can process a lot of data, probably not as fast as these computer systems can, but it is kind of matching that capability. It's allowing it to learn from large amounts of data. Not we're again here, don't think Excel, think about massive amounts of data. Essentially, Chat GPT 3.0 was trained on the internet. And if you can think about that, it took many years of all of the data it could find on the internet and fed that in as the input. I mean, it's incredible the amount of data that it takes as you go through that, which is why a modern computer center, these ultra scale computer centers, take as much electricity as a small city. not just for the computational energy, but for the cooling and energy with regard to so these chips don't burn themselves out. But these data centers are now a leading growth area in electricity demand. And so they're really, and they're not your while the GPU chip is a huge advancement on a CPU chip, we're now putting thousands of these things in racks, within these centers with regard to that. So these deep learning drive many artificial intelligence applications to improve automation, performing analytical and physical tasks, i.e., robotics. That's when we kind of connecting it here to physical tasking. So, well, what is a robot doing in the oil field? Well, it's handling pipe on a drilling rig, or it's automated Kelly on a drilling rig. So we are now trying to control physical tasks through all of this stuff as well. So, essentially, we are now well into this world. There are different ways to train machine learning models. A supervised learning approach is very much like our history matching on our current reservoir simulation sort of techniques, where we essentially take a part of the data, our historical data out, and we train the algorithm with 80% of the data, and then we test it back in with 20% of the data. That supervised learning, and somehow, whether it's through labeling, whether it's through classification schemes or whatever, whether it's through regression schemes or what techniques, we are essentially sitting over the model to tell it that's a good answer, that's a wrong answer, or that is a different sort of answer. Let me investigate it further. That is where most of the work is going right now, is through supervised learning of some sort of machine learning kind of technique like neural networks. There are some people now who are beginning to say, maybe I don't need to tell it what the right answer is. Maybe I'm just going to let it try to figure out through correlation what the right answer should be. And that's unsupervised learning. And there's some very interesting results coming out of those that are trying that unsupervised learning sort of an approach. There's also some fantasy coming out of that. That's also where, in some places that either, through biased data sets or through just some of this unsupervised learning, that you can get the hallucinations kind of answers as it goes through this. But again, you're trying to, under the supervised learning, this is where we have the hybrid models where we put the physics-based constraints, and the unsupervised learning is when we take those off. It kind of gets to a couple of important kind of themes here as I begin to kind of close. But what now is the role of the human being, the human operator, when we have these automated systems? When we have the model being built by an AI machine learning kind of an approach. It is learning from its system. Well, what does the human being do now? Well, I think this doesn't replace human beings. Human beings are very, very important at the beginning, i.e., feeding it the right data to train it on, and but then also to deal with the intervention, with the outliers, the unusual circumstances that the algorithms don't recognize very well, and also to kind of as an overseer of the entire model about trying to say where it may steer from reality, or maybe it produces some insights that the humans didn't think that system had, and it needs to make a whole bunch of adjustments because of that. So this is not a replacement of the human being. This is a different role for the human being. Well, just again, the last kind of thing from Dr. Sankaran. And again, he's talking about the advances in machine learning based in the convolutional neural networks. There's one of the, kind of the more physical constrained models. So what we are trying to do is have a little bit of both worlds. We're trying to put some of these physics constraints within the algorithm development. We're trying to kind of, in a sense, pick and choose and label the data that we feed into these things, being what we think are the most appropriate, most trusted data. We're trying to come in here and figure out what are the right data elements to build our model, because we're winnowing down through principal component analysis sort of things. So that, and we're getting to this whole idea of the hybrid model. Dr. Sankaran is very, very big on this idea of thinking about everything as physics and statistics. And the statistics has taken this next level kind of jump into machine learning in order to try to work all of this stuff together. And it is all of these things. It's not one or the other. It is all of these things that really create the data-driven models for process automation and control. And frequently, the more sophisticated plant control sort of systems are come from downstream. They come from a refinery. They come from a factory, or whether it's where that's where they have kind of improved those sort of processes and built them up. But the one thing different between a plant and the oil field is the degree of uncertainty. Plant, we pretty much know the inputs, we know the outputs, there's a regular process, and it is more of an automation sort of problem. Although there are changes in the what we want to make out of the refinery, or there are changes of what we might want to put in terms of the inputs. The oil field is very different in the fact that we never built the reservoir. We only have indirect measurements of some of the attributes of the reservoir. So the reservoir is one major source of uncertainty within all of our processes as upstream, where we continue to have to learn to live with that degree of uncertainty as we go forward. I see that there's several things in the chat. Just let me finish a couple slides and I'll jump into those. But again, some of the kind of aspects here of what are our challenges. We have lots of information now, data now, but a lot of it doesn't have the same context. We can't relate it back into that digital twin integrated model. We have limited cross-functional collaboration. We still do not work in the kind of broader teams that now this digital oil field 4.0 might allow us to do. The need for niche expertise is still there, but how do we integrate them into the teams that we want to try to take a look at? Our models are still backward looking, not forward looking. They are still too rigid for some of the dynamic things that happen. And we are still reacting to events, be they engineering events, reservoir events, economic events, whatever it is. And we still are improving our efforts on a silo. We're learning how to drill a better well, but not really learning how to turn that into better reservoir management. But with all of the hype, management still thinks this is going to be magic and it's going to change the world. It is changing the world, maybe not as fast as management wants it to be, or certainly not as fast as some of the tech companies think it should be. Well, and we've got some very interesting kind of exceptions. The whole idea that you can read about deep fakes. We can now use this generative AI to create things that never existed. We can intentionally induce bias or fantasy into some of our models. And now that we can create text, we can create lyrics to a song, we can create poems, we can create images, we can now begin to change history into fantasy. And so clearly we're now to the point where the computational capabilities are very significant. What's the practical use for this stuff? This, in 1940s, this is what AI looked like. This is the Enigma machine that the British mathematicians used to try to crack an encrypted German military code in order to try to intercept what the Germans were trying to do against Britain in World War II. This is Alan Turing's technology with regard to it. This is where it kind of got started and now we have what we have. So it has grown up relatively quickly, maybe about 80 years worth of history, but it is again kind of on an exponential learning curve. The data we are dealing with, when you start to be, we are pretty rooted in historical fixed kind of equipment, data sources. But now when we get into real-time data, and we have to begin to look at how we show this data and how we show uncertainties in this data. So this whole idea of how to deal with real-time series data sources is a very large new player on the block versus our historical data. So when I have a data point every second, and maybe it has some sort of cyclical behavior like this, kind of diagram, or maybe it doesn't. And what does it have to do when it gets out of the bounds or whatever? How do we interpret all of this? And again, in a very dynamic kind of way. We're not creating a report and that is the answer. We're creating a view that will change, within the next sample rate. We need to look at the algorithms, the techniques. I mean, that's where an awful lot of focus is going into right now. But we need to also figure out its impact on operations. We need to impact this level of sophistication. We need to understand how we are going to manage this. What is the role of the human being? The user personas, in a sense. We don't have jobs anymore. We have personas, right? And we could have, as an engineer, several different personas to based on our role on our teams with regard to all of these things. But now it is thoroughly changing, potentially thoroughly changing everything we try to do, because all of this stuff can be a a real revolution. I mean, a lot of the changes we have made over the past 20 years, I would consider as evolution of many of the techniques we've been doing in the future. But potentially it ends up in something that is revolutionary with regard to how we manage oil and gas. Well, this slide, I mean, again, it talks about the changing nature of analytics. Back in the early days, we just wanted to know what happened. And now we're to the point where we want to know, why did it happen? What is likely to happen given current operating positions? But, uh, but now, again, that future prediction task, where I think a lot of us want to go, a lot of management wants us to go. It's the idea, what is it going to take to make good things happen more often? How do I go from P50 to P80? Yeah, how do I understand? I always have higher production and lower water production and take advantage of price, sort of changes. And how do I do all of that stuff most of the time? That is the optimization problem that I think we have within all of this. And again, to emphasize, it's a team, it's collaboration. It is the math and statistics knowledge, it is the data handling skills, it is the domain knowledge, which is largely the petroleum engineer. And as essentially it takes all of this. It's not one or the other. It's not some programmer who comes in here and all of a sudden figures out how to produce oil and gas. It is this collaboration that's going to help us do this. Now, here's the slide I talked about before. For for decades, one of the key parameters that we judged the health of the oil and gas industry was the number of rigs that were out there drilling. And here you see in the blue, from a period of it's from 1980 to now, essentially the number of rigs that were drilling in the United States. And as you can see, there's, certainly from about 2005 to now, there's been a pretty steady decline. And so does that mean the oil industry is in decline? Well, look at the white curve. That's U.S. oil and gas oil production. And as during this period of time when the number of rigs went down, the amount of oil went up. Well, what's the real goal? The real goal is oil production at a profitable price. We haven't figured in operating costs here yet. But essentially, we've been able to grow the production of these fields, mostly shale fields in the U.S., through fewer and fewer rigs, drilling rigs. That's productivity, measured through us. That is a tremendous success. If you look at the old parameter of number of drilling rigs, it's the wrong parameter anymore. But it is now the oil production per rig, which is dramatically improved, largely because of a lot of the statistical techniques of looking at how to drill a directional well, how to drill and frack a well, productively to get more oil and gas out of the ground faster. All of this is a success of data science and engineering analytics. But it also changes what is the parameter, success parameter that we need to measure as we go forward. More and more companies are using AI. I mean, you go to SBE groups and other sort of things. There are now whole sections talking about some of these models that are being built. And there's a lot of very clever new programming. There's a lot of really clever new use cases which are talking about how to use these models to improve efficiency as you go through this. So this is today. This is tremendous impact. It's not a, I need something I might want to use sometime in the future. And here are kind of the last words from Dr. Sankaran that I totally agree. Data science is now a must to have skill. It is not a nice thing to have. Petroleum engineers now have to be programmers as well as good petroleum engineers. My last class, I actually gave a homework assignment not a final class project, but a homework assignment to take a data set, go through a artificial neural net model using a Python code library, and essentially come up with the answer for this. This was a homework problem. This is not a new advanced degree, and this is for undergraduates. This was a senior level, kind of an exam. This is now what is expected of engineers. And I think though those just coming out of university have an advantage in a way that they probably get this stuff in many of their courses, or they have the learning resources available to them. Oh no, an engineer that was went through school 10, 15 years ago, we weren't talking about this. This was a brand new thing. They have to go back and try to figure out how to catch up with the engineer that just graduated as you go through this. So, according to Dr. Sankaran, this is the number one driving force for personal development in the workplace. Now, if you didn't get it in class, somehow you have to make it up. I should have used a cricket player given this audience here, but I don't have a good enough meme from a cricket player to be able to put here. So this is an American baseball player. Um, and his quote was, "The future ain't what it used to be," and that is about as good as I could sum up all of this, kind of progress from these different things. What we used to consider in a as good reservoir management or good production optimization or good drilling from a conventional resource 10 or 15 years ago, that future ain't what today's future is all about. So thank you, and let me jump into the chat and let's see if I can handle a few questions.